Have you ever wondered how a seed learns to fly? Not with feathers or engines, but with pure geometry, air, and time. Welcome to Foe's Curiosity, where we uncover how nature's silent inventions can teach us the art of engineering. Today, we're diving into one of the most elegant examples of natural flight, Anemochory, the way plants use wind to disperse their seeds. It's a story of evolution, physics, and aerodynamic genius, crafted not by human engineers, but by trees and flowers trying to spread their offspring across the world. Let's start with a simple scene. Imagine standing in a meadow during late summer. The wind stirs, and thousands of tiny parachutes lift from the earth. Dandelion seeds, each no bigger than a whisper, rise, drift, and vanish into the horizon. They have no muscles, no propellers, no onboard computer, and yet they fly. How?
The answer begins with a biological imperative: dispersal. For plants, staying close to home is risky. If all the offspring land in the same patch of soil, they'll fight for light, nutrients, and space. So, evolution found a way to outsource their travel to the atmosphere. This is Anemochory, the art of riding the wind. Every airborne seed is an aerodynamic compromise, a masterpiece of natural engineering tuned to one key goal: maximize time aloft. The longer a seed stays in the air, the farther it can travel. To achieve that, nature minimizes a quantity called terminal descent velocity, or UT. The speed at which gravity pulling down is perfectly balanced by the lift and drag holding the seed up. The lower this velocity, the gentler the fall, and the greater the distance it can ride the wind. But this isn't one-size-fits-all flight. Seeds have evolved a remarkable diversity of shapes and strategies: flyers, rollers, throwers, and within the flyers, distinct aerodynamic designs: the dust-like spores that float invisibly, the plumed parachutes like dandelions, and the spinning wings of maples known as samaras. Each design tells a different aerodynamic story. At the scale of seeds, air behaves differently. The Reynolds number, a measure of how much viscosity dominates a flow, drops into the low thousands, even down to 1. At these tiny scales, air feels more like honey than a free-flowing gas, and that changes everything. Seeds can't rely on brute momentum or fast airflow. They have to manipulate vortices, tiny whirlwinds of pressure and motion. Take the maple samara. As it falls, it begins to spin like a helicopter blade. This auto-rotation stabilizes its descent and, crucially, generates lift. The secret lies in a phenomenon called the Leading Edge Vortex, or LEV, a swirling zone of air that clings to the seed's curved edge, generating a surprising amount of upward force. By maintaining that vortex just below the point of flow separation, the maple seed effectively cheats gravity, descending slowly and gracefully, its one-sided wing perpetually slicing through the air. It's not just pretty, it's optimized. Studies show that the precise curvature of the samara wing isn't random at all. It's tuned for the lowest possible descent velocity. The ideal fold angle, the way the nut connects to the wing, even the curvature distribution, all of it balances lift and drag to perfection. Then there's the dandelion, perhaps nature's most successful aeronautical engineer. Its seeds don't spin, they float. The secret weapon here is the pappus, a delicate ring of filaments that acts as a porous parachute. You might think that having holes would make it worse at catching air, but it's exactly the opposite. At just the right Reynolds number, air flowing through and around the pappus forms a stable, separated vortex ring, a donut-shaped whirlpool of air that hovers just above the seed. This ring creates a low-pressure zone, dramatically increasing drag and keeping the seed steady. Computational models have shown that the pappus's porosity is tuned almost perfectly. If it were any denser, the flow would detach chaotically. Any looser, and lift would collapse. The result is astonishing stability. The dandelion seed can remain airborne long after denser seeds have dropped, riding faint updrafts that can carry it kilometers away. Some plants, however, take a more aggressive approach. The hairy flower wild petunia launches its seeds like miniature bullets. These peppercorn-sized projectiles are fired at speeds of about 10 meters per second, and spin faster than anything else in nature, over 1,200 revolutions per second. This backspin creates gyroscopic stabilization, keeping the seed perfectly oriented during flight. It's the same principle that keeps a spinning top upright, only here it's used to minimize drag and extend range. While dandelions aim for long suspension, petunias aim for long range. Different strategies, same evolutionary goal. Across ecosystems, these mechanisms have appeared again and again, independently, proof of convergent evolution. Maples, ash trees, dipterocarps, and even desert shrubs have all reinvented the spinning wing. The Asteraceae family, the daisies and dandelions, perfected the plumed parachute. Nature repeatedly converges on these aerodynamic designs because the laws of physics reward them. When air and gravity are the sculptors, form inevitably follows function.
There's a beautiful paradox here. While natural selection pushes seeds toward the lowest possible descent velocity, evolution doesn't demand one perfect shape. There are many ways to achieve good flight. The maple's wing, the petunia's spin, the dandelion's parachute all arrive at the same aerodynamic outcome through different morphological paths. This flexibility is one reason wind dispersal appears in so many unrelated plant lineages. And these ancient air travelers are now inspiring something new: engineers. Researchers have built micro-aerial vehicles, MAVs, that borrow directly from these seed designs. A maple seed-inspired monocopter weighing just 32 grams has managed a controlled hover for over 20 minutes using only one actuator. It's energy efficient because, like the samara, it uses passive stability and natural lift instead of constant power. Others are experimenting with biodegradable 3D printed microseeds that could carry environmental sensors, drifting across forests or even alien planets. Imagine hundreds of tiny devices floating through the air, measuring humidity, pollution, or radiation, powered by nothing more than the wind, the dandelions of technology. But translating biology into engineering isn't as simple as copying shapes. Testing these microflyers in labs is tricky. To accurately model seed flight, scientists must match dimensionless numbers, like the Reynolds number, which controls how air flows, and the Froude number, which balances gravity and inertia. The problem is that you can't always match both at once in a wind tunnel, a conflict known as the Reynolds-Froude dilemma. Specialized methods, like wind tunnel to atmospheric mapping, help bridge that gap, ensuring small-scale models behave like their real-world counterparts. What all this tells us is that nature is an unparalleled aerodynamic engineer. Seeds are not passive specks. They are refined flying machines that manipulate invisible currents with the precision of drones. From the spiral of a maple wing to the floating vortex above a dandelion, every detail has been shaped by the atmosphere itself. And as we learn from them, we begin to imagine our own future in flight, one that doesn't fight the air, but collaborates with it. Imagine this. You're standing on the edge of a cliff, wind rushing past your face, looking down at the vast world below. You take a deep breath and jump. What would it take for you, not a bird, not a bat, not an insect, but you, to actually fly? Flight isn't just motion, it's rebellion against gravity. To stay aloft, an organism must master a delicate balance of 4 forces: lift, thrust, drag, and weight. Lift and thrust keep you up and moving forward. Drag and gravity constantly pull you down. Every bird, bat, or insect is engaged in a perpetual duel with physics itself. But not all things that glide through air are truly flying. There's a strict scientific distinction here. Powered flight means generating thrust through your own muscles, beating wings to push air backward and stay airborne. Gliding, on the other hand, is merely controlled falling. A flying squirrel or a paper airplane doesn't fly, it converts height into distance. Soaring, like that of eagles or albatrosses, is clever cheating, using rising air currents to stay aloft without burning much energy. And then there's ballooning, the delicate dispersal of spiders that release silk threads and let the wind carry them like tiny airborne explorers. Each of these modes uses the air differently, but only powered flight, true, sustained, self-propelled flight, lets life fully conquer the sky. So, who cracked this code? Only 4 groups ever managed it: insects, pterosaurs, birds, and bats.
4 times in Earth's 3.8 billion year history, evolution independently solved the same grand challenge. That's convergence on a cosmic scale. The first pioneers were the insects, around 350 million years ago, during the Carboniferous period. Imagine forests filled with giant ferns and dragonflies the size of seagulls, like Meganora, with a wingspan over 70 centimeters. These ancient titans of the air thrived in an oxygen-rich atmosphere that supercharged their simple respiratory systems. Their success in taking to the air reshaped ecosystems forever, turning the skies into new territory to hunt, mate, and escape predators. Then came the pterosaurs, the first vertebrate flyers, arriving much later, about 228 million years ago. Their wings, vast membranes stretched between elongated fingers, made them masters of prehistoric skies.
Eventually, birds and bats followed, each taking radically different anatomical routes to the same destination. But what evolutionary pressures pushed animals toward flight in the first place? Flight offers irresistible advantages, escaping predators, reaching new habitats, and finding food others can't. Once one lineage discovered even a hint of aerial control, natural selection had every reason to push it further. Two major ideas explain how that push happened. One theory, directed aerial descent, imagines creatures that first leapt from trees, gliding and steering toward safety. The other, the fundamental wing stroke hypothesis, flips that logic. Maybe wings started not for gliding, but for power, flapping to help climb, leap, or stabilize during jumps. Fossil evidence from ancient insects supports the latter idea. Early pterygote nymphs already had articulated wings, not fixed gliding surfaces, but movable appendages capable of active flapping. In other words, from the very beginning, flight may have been muscularly powered. Evolution didn't start with a glide, it started with a beat. That leads us to one of evolutionary biology's most fascinating debates. Where did insect wings actually come from? One camp argues for the perinodal hypothesis, that wings evolved from stiff extensions of the body wall, perhaps used for gliding or display. The other, now better supported, is the excite hypothesis, that wings came from small mobile outgrowths of ancestral legs, structures that once functioned like gills or flaps. Modern genetics backs this up beautifully. The same genes that pattern wings in fruit flies, Apterus and nubbin, also activate in the leg-like appendages of crustaceans. It means that wings weren't built from scratch. Evolution repurposed an existing toolkit. The muscles and nerves needed for movement were already there. Nature just moved the machinery upward and flattened it into a new structure capable of flapping. From those ancient leg gills came flight. Now let's zoom out to the physics that governs it all. The air doesn't care about your evolutionary story. It only cares about scale, speed, and force. Enter the Reynolds number, a ratio that determines how air behaves around a moving body. Small creatures like gnats and bees live in a world where air feels thick and sticky, dominated by viscous forces. They fly in what's called a low Reynolds number regime, where traditional aerodynamics, like the kind used to design airplanes, simply doesn't apply. To survive here, insects exploit unsteady aerodynamics. They do things planes can't. Their secret weapon? The Leading Edge Vortex, a tiny spiral of air that forms over the wing with each stroke, boosting lift at extreme angles. Add in rapid wing rotation and weight capture, the reuse of air disturbed by previous strokes, and you've got the recipe for aerial agility that no human machine can match. Insects surf the chaos. Large vertebrate flyers, on the other hand, operate at high Reynolds numbers. Air flows smoothly over their wings, and they rely on quasi-steady lift, much closer to what airplanes do. Birds and bats optimize their wings for efficiency, stability, and control. The same equations that let engineers design jets apply here too, but with one key difference. Evolution never had blueprints. It learned by survival. But there's a hard limit to all of this. The square cube law, first noted by Galileo, sets an upper boundary on what flight can achieve. As a body grows larger, its mass increases by the cube of its length, while surface area, and thus wing area and muscle cross-section, grows only by the square. The result? The bigger you get, the worse your lift-to-weight ratio becomes. That's why the largest known flyers, like Quetzalcoatlus northropi, the enormous pterosaur, maxed out around 250 kilograms. Beyond that, biology hits a wall. Wings would need to be impossibly large, muscles too powerful to sustain, and heat generated from flight too intense to manage. A flying elephant isn't just improbable, it's physically impossible. Even if you gave an elephant wings the size of a football field, its body mass would demand so much lift that its bones would snap before it even took off. Evolution knows the math, and math, in this case, doesn't negotiate. Across hundreds of millions of years, life has danced with physics to conquer the air 4 separate times. Insects, pterosaurs, birds, and bats, all masters of the same game, but each using their own rules. The story of flight isn't just about wings, it's about constraints, about how life continuously pushes against the edges of what's physically possible, and sometimes, just barely, breaks through. But the story doesn't end here. Have you ever wondered how life learned to master the sky?
From the shimmering wings of ancient insects to the leathery sails of pterosaurs, from the feathered elegance of birds to the supple membranes of bats, each group took a completely different evolutionary road, yet arrived at the same destination: powered flight. So, how did these creatures, separated by hundreds of millions of years, solve the same problem in such astonishingly different ways? Let's start where all flight begins, not in the sky, but on the ground. Long before birds ever soared, there were small, feathered dinosaurs experimenting with the air. The story of how they took off has sparked one of evolution's great debates. Some scientists champion the arboreal, or trees-down hypothesis. Picture small, tree-dwelling dinosaurs gliding from branch to branch, their primitive feathers acting as parachutes. Over generations, better control led to longer glides, until one day, those controlled descents became true flapping flight. Others favored the cursorial, or ground-up hypothesis. Imagine fast-running dinosaurs using their feathered arms for balance and lift, much like a runner using outstretched arms to steady themselves. Each leap became a little longer, each flap a little stronger. And then there's the pouncing proavis model, suggesting that feathers first evolved to help predators leap down on unsuspecting prey with precision and control, aerial ambush specialists before they ever became flyers. Today, most researchers think it wasn't one story, but many. Early avialans likely lived in mixed habitats, sometimes climbing, sometimes running, sometimes gliding, and natural selection built on every small advantage until real flight took shape. One particularly clever link between running and flying is called wing-assisted incline running, or WARE. Young birds today use this trick to escape predators by running up steep slopes, flapping their wings to press themselves against the surface for grip. It's a beautiful behavior bridging the gap between ground and air, but there's a twist. Fossils show that early birds like Archaeopteryx lacked the specialized shoulder mechanics needed for that powerful upstroke. So while WARE might explain how modern birds use their wings this way, it may not tell the full story of how flight began. What's clear is that by the time of Archaeopteryx, about 150 million years ago, the key ingredients were already taking shape. Its wings show the geometry of true flapping flight. Even if its breastbone, the anchor for flight muscles, was still under construction. Evolution had the feathers before it had the engine. And those feathers, what a story they tell. Feathers didn't evolve for flight at all. They began as proto-feathers, fuzzy filaments for warmth, display, or camouflage. Over millions of years, they grew more complex, hollow tubes sprouting barbs, then branching into flat veins that could catch air. The magic came when those veins began to zip together with tiny hooks, forming a coherent surface, a perfect natural airfoil. But flight demanded more than shape. It required the right material. Early feathers were made mostly of alpha keratin, soft and flexible. Modern flight feathers are built from beta keratin, a tougher protein that can withstand the enormous stresses of flapping. One fossil, Anchiornis, shows us this critical transition: beautifully shaped feathers, but made of the wrong keratin. Proof that even after evolution got the design right, it still had to perfect the chemistry. So, feathers began as insulation, became ornaments, and ended up as engines of flight, one of the most astonishing examples of exaptation, where evolution retools old parts for new purposes. But let's rewind even further.
hundreds of millions of years before the first bird, because the skies already belonged to another master: insects. Insects were the first animals to conquer the air, sometime around 300 million years ago. Their wings evolved not from arms or legs, but likely from gill-like outgrowths on the thorax, structures that once helped aquatic ancestors breathe or swim. Over time, those flaps caught the wind. And what truly set insects apart wasn't just how their wings evolved, but how they moved them. Early dragonflies used direct flight muscles, each wing moved by its own muscle. Simple, powerful, but limited to about 100 wing beats per second. That's already impressive, but evolution wasn't done innovating. Later insects developed indirect flight muscles, attached not to the wings themselves, but to the exoskeleton. When these internal muscles contract, the thorax deforms, causing the wings to flap up and down like a resonating spring. And then came the breakthrough: asynchronous muscles. Instead of firing once per nerve signal, these muscles are triggered by stretch, meaning one contraction mechanically triggers the next. The result? Tremendous speed and efficiency. Some flies beat their wings over 1,000 times per second. It's one of nature's most elegant engineering tricks, turning biological tissue into a self-oscillating machine, limited not by the speed of nerves, but by the physics of resonance. Next, we glide forward in time to the Mesozoic skies, the age of pterosaurs, the first vertebrates to achieve powered flight. They ruled the air long before birds did, with vast wings stretched over a single elongated finger. Their hollow bones were light but strong, filled with air sacs that made even the largest pterosaurs, creatures with wingspans over 10 meters, light enough to soar. When birds evolved later, they independently reinvented that same trick: lightweight, pneumatic bones, and complex lungs that circulate air continuously. Different lineages, same physics. That's convergent evolution, the universe whispering the same solution into different ears. And then, much later, came the bats, the only mammals to truly fly. Unlike birds, bats stretched their own hands into wings. Their fingers, long, slender, and flexible, support a living membrane of skin. It's a marvel of biomechanics, rich in blood vessels and nerves, giving bats extraordinary control over shape and movement. Their flight is agile, almost liquid. They can twist and fold their wings mid-air, creating swirling vortices that give them lift even during the upstroke.
But every design has trade-offs. Birds, with their rigid feathered wings, are more efficient over long distances. Bats, with their flexible membranes, sacrifice speed for precision. Yet that very flexibility lets them snatch insects in darkness, hover beside fruit, or carry prey half their weight straight from the ground. Evolution doesn't chase perfection, it builds specialists. When you look at all these flyers together, insects, pterosaurs, birds, and bats, a single truth emerges. Gravity is a universal teacher. It sets the same exam for every lineage, and although the answers differ, the principles are the same. Every flyer must overcome the same constraints: reduce weight, generate lift, produce thrust, and minimize drag. Evolution solutions, light bones, air sacs, efficient muscles, aerodynamic surfaces, are not coincidences. They're the inevitable physics of life confronting air. Flight didn't appear overnight. It unfolded over hundreds of millions of years.
Insects took off first in the Carboniferous. Pterosaurs followed, gliding through Triassic skies. Birds emerged in the Jurassic, refining feathers into perfect wings. Each time, evolution faced the same impossible question: how can life defy gravity? And each time, it found a different but equally astonishing answer. Every time a bird takes off, it performs an act of continuous negotiation between gravity, lift, thrust, and drag. 4 invisible forces that must stay perfectly balanced. Gravity tries to pull the bird down. Lift, generated by its wings, pushes it up. Thrust propels it forward, while drag fights back. Flight, then, is not a single act of power. It's a conversation between these forces, managed second by second by the bird's anatomy and brain. The secret begins in the shape of the wing. When air flows over its curved upper surface, it speeds up, creating a region of lower pressure. Meanwhile, the slower air beneath pushes upward harder. That difference in pressure creates lift, as described by the Bernoulli principle. But there's another story here, Newton's third law. As the wing pushes air downward, the air pushes the wing upward. In truth, both principles work hand in hand. Lift exists because the wing turns air downward, and that downward flow generates the upward force we call flight. Now imagine a bird banking into a turn. It subtly increases its angle of attack, the tilt of the wing relative to the oncoming air, forcing more air down and producing more lift. But too much angle and the airflow separates, the wing stalls. Yet birds can dance right at that edge of stall without falling, a balance no airplane could achieve so gracefully.
This is where wing morphology comes in. Not all wings are built alike. An albatross, gliding endlessly over the ocean, has long, narrow wings with a high aspect ratio, perfect for minimizing drag and maximizing efficiency. A sparrow, darting through city streets, has short, broad wings. Less efficient, yes, but ideal for agility and rapid maneuvers. Every species strikes its own compromise between speed, stability, and control. Evolution is a master engineer, always optimizing for survival, not perfection. And the magic doesn't stop at the bones. Birds' wings aren't rigid like airplane wings. They morph. Through a process called camber morphing, birds can flex and reshape their airfoils in real time. By adjusting curvature, they tune the balance of lift and drag on demand. It's flight control that puts modern aircraft flaps and ailerons to shame. Engineers have tried to copy this trick, designing morphing wing drones that change shape mid-air for efficiency. Direct inspiration from nature's blueprint. But perhaps the most unsung heroes of flight are feathers. They're not just decoration, they are aerodynamic masterpieces. The primaries at the wingtips act like propeller blades, slicing air to generate thrust. The secondaries closer to the body form the lifting surface. Together, they create a flexible, self-healing, and remarkably efficient system. At the front edge of the wing sits the alula, a tiny cluster of feathers that acts like a built-in anti-stall device. During slow flight or landing, when the bird tilts its wings sharply, airflow threatens to break away. The alula pops up, stabilizing a swirling pocket of air called a leading edge vortex, which clings to the wing and sustains lift. It's like having a miniature vortex generator, keeping flight smooth even under extreme conditions.
Even individual feathers show exquisite design logic. Each has a subtle twist that helps regulate aerodynamic torque, preventing chaotic flutter during fast flapping. It's a kind of passive control system built right into the material, one that engineers dream of replicating in flexible drones. Then there's the tail, an aerodynamic multi-tool. It acts as a rudder, elevator, and brake all at once. During takeoff and landing, the tail can generate up to 30% of total lift. Its geometry allows even small motions to create big changes in pitch and yaw, giving the bird fine-tuned control over direction and stability. Spread wide, it can stop a bird mid-air like an air brake. Tilted slightly, it can redirect airflow for sharp turns. But it's not only wings and tails that shape performance. Even the head and beak play aerodynamic roles. The sharp, pointed beak of a heron cuts through air with minimal drag. Some species have microgrooves, tiny riblets along their beaks that reduce turbulence, much like the textured coatings used on racing aircraft and sharkskin-inspired swimsuits. Nature has been refining drag reduction millions of years before humans discovered fluid mechanics. And what about the neck? Long-necked birds like swans use it as a mechanical stabilizer. As their bodies bounce with each wing beat, the neck moves in the opposite direction, acting like a spring damper system. This keeps the head and the bird's gaze remarkably steady, even in turbulence. It's like having a built-in gimbal for vision, allowing precise control of flight path and balance. All these adaptations combine to support the many modes of flight. Flapping flight, the most familiar, generates both lift and thrust with each beat, but it's also the most energy-hungry. Hovering, the ultimate feat of powered flight, is even more demanding. Hummingbirds manage it by producing lift on both the upstroke and the downstroke, their wings beating up to 80 times per second. Their flight muscles are extraordinary. The ratio of their downstroke to upstroke power muscles is nearly 2 to 1, meaning they generate immense lift even as they reverse direction. Then there's gliding, unpowered descent. A gliding bird trades altitude for distance, maintaining just enough lift to counter its weight. And soaring, the art of using the sky's energy for free. In thermal soaring, hawks and vultures ride invisible columns of warm air that spiral upward. In dynamic soaring, albatrosses harvest wind shear above the ocean, using the difference between fast and slow air layers to fly thousands of kilometers without flapping once. It's like surfing the sky's invisible waves. Behind every flight style lies a deep physiological foundation. Birds have hollow bones, vast lungs, and high-performance circulatory systems. Their hearts are oversized for their bodies, pumping oxygen-rich blood to fuel the incredible metabolic demands of flight. The power-to-weight ratio of a bird's flight muscles puts many small aircraft engines to shame. And just as engineers talk about power curves, birds too live by them. The power required to fly changes with speed, forming a U-shaped curve. Flying too slowly burns energy fighting gravity. Flying too fast burns energy battling drag. Somewhere in the middle lies the sweet spot, the minimum power speed for endurance, and just beyond it, the maximum range speed for distance. Birds instinctively find these zones, adjusting their flapping frequency to match. Even here, nature surprises us. Studies show that when birds fly together, say in synchronized flocks or tandem pairs, they sometimes abandon this efficiency curve.
So what do we learn from all this? That avian flight is not just motion, it's a masterpiece of adaptive engineering. Every feather, muscle, and movement plays its part in balancing physical laws and biological needs. It's a design so robust that it thrives in storms, deserts, and oceans, and yet so elegant that it makes human flight seem clumsy by comparison. From passive feather stability to dynamic tail control, from morphing wings to self-stabilizing necks, the physics of bird flight continues to inspire modern aviation, especially the next generation of bio-inspired drones capable of flying efficiently in unpredictable, turbulent airspaces. And the story doesn't stop here, because if air can shape the evolution of birds this profoundly, what else does it shape? From the dizzying flight of bats and birds to the floating journeys of pollen and spiders, the aerosphere is not just the backdrop to life, it's an ecological stage, a selective force, and even an evolutionary engine. So let's breathe in the science behind it. Imagine the layer of air just above the ground, the space where wind gusts dance, turbulence stirs, and electric fields hum quietly across the sky. That's the aerosphere, a dynamic three-dimensional habitat where temperature gradients, wind velocity, and even the global electric field, the atmospheric potential gradient, set the rules of survival.
This is the domain of aeroecology, a science that asks, how do living things sense, exploit, and evolve within air itself? From the smallest insect to the largest eagle, air shapes their bodies, refines their senses, and directs their behaviors. Evolution has sculpted wings, hairs, and antennae with surgical precision, all to navigate this invisible fluid medium. Let's start with the senses, the first step in mastering the sky. Insects, for example, don't just feel the breeze, they read it. Tiny hairs on a locust's head detect minute shifts in airflow, signaling when to tilt, turn, or stabilize mid-flight. Antennae, often thought of only as smell organs, are actually incredible multi-tools. They sense not just chemicals, but heat, sound, and, crucially, air movement. For a moth tracking a faint scent in a turbulent wind, those antennae become both compass and radar, guiding it for a chaotic three-dimensional maze of odor plumes and invisible currents. Bats take this to another level. Their wings aren't just for flight, they're sensory arrays. Across the membrane stretch microscopic hairs, each connected to sensitive nerve endings that detect the tiniest reversals in airflow. When air begins to separate from the wing, signaling a potential aerodynamic stall, these sensors fire an instant warning to the brain. The bat corrects its motion in milliseconds, dodging obstacles, banking sharply, or hovering with precision. Remove those hairs, and the animal's agility collapses. That's how vital this stall detection system is.
It's evolution's own version of a high-tech flight control sensor, tuned by millions of years of trial and error. Even birds, descendants of ancient air-traveling reptiles, carry a legacy of sensory adaptation. Their ability to detect shifts in atmospheric pressure may trace back to ancestral aquatic species like sharks. While we humans sense weather changes only when the rain begins, birds feel them coming through their baroreceptors, adjusting their migration paths long before a storm arrives. The air, in other words, speaks, and animals have learned to listen. Now let's talk motion, how life uses air not just to move, but to move wisely. Soaring birds like eagles and vultures have mastered the art of flying for free. When the sun heats the ground, warm columns of air, called thermals, rise upward. By circling within these invisible elevators, birds climb thousands of meters without a single wing beat. Over mountains, the story changes. The wind slams into slopes and deflects upward, creating orographic lift. And far out to sea, some species perform dynamic soaring, slicing through layers of air moving at different speeds to extract energy from the wind itself. It's like surfing waves made of sky.
Even insects understand these principles. Radar studies show that migrating swarms don't drift randomly. They counteract rising air to hold steady altitude, conserving energy and maintaining formation. The atmosphere becomes not a hazard, but a finely tuned transport network. Air also shapes communication and navigation. Odors in turbulent air don't spread as smooth gradients. They break into filaments, thin, intermittent streaks of scent. For a moth or a crab, following a smell means dancing through bursts of odor, steering between empty patches, guided by mechanical cues of airflow more than by chemistry alone. It's an exquisite duet between biology and fluid dynamics. Plants, too, are quiet engineers of air. Leaves, for instance, don't just absorb sunlight. They negotiate constantly with the surrounding atmosphere. Their survival depends on regulating heat and gas exchange through microscopic pores called stomata. But a thin boundary layer of still air clings to the surface, trapping heat. The solution? Fluttering. When a breeze hits, flexible leaf stems let them quiver, breaking that boundary layer and enhancing cooling through convection. In fact, experiments show that a fluttering leaf can transfer up to twice as much heat to the air as a rigid one. So next time you see a trembling tree canopy in the wind, know this: it's not random motion. It's a self-cooling, self-regulating thermal system, perfected by evolution. But air isn't only about movement. It's also a medium of reproduction and migration. Take wind-pollinated plants. Their flowers are often plain and scentless, but their pollen grains are aerodynamic masterpieces. Some, like those of pines, carry tiny air bladders called saci that increase surface area without adding much weight. This reduces their settling speed, keeping them aloft longer and extending their reach across forests and valleys. Meanwhile, spiders have evolved a far stranger method of flight: ballooning. They climb to a high point, raise their abdomens, and release silken threads that catch the wind, sending them sailing through the air. For years, scientists assumed it was just aerodynamics, but recent experiments revealed another force at play: electrostatics. Earth's atmosphere carries a natural electric field. When spiders release silk, the threads gain a negative charge and interact with the positive field above, creating lift. Under normal conditions, about 1 kilovolt per meter, a spider weighing less than a milligram can rise into the air purely on electrostatic force. In calm weather, when wind isn't enough, electricity takes over. It's a hybrid strategy, combining the physics of wind and charge, a biological bet hedging system evolved for unpredictable worlds. Zoom out, and you start to see the aerosphere for what it really is: an engine of evolution. Every flap, drift, and glide shapes life itself. Air's constant variability, its shifting currents, storms, and temperatures, selects for flexibility. It rewards organisms that can sense, respond, and adapt in real time. Birds that miss time migration lose entire breeding seasons. Plants that can't adjust pollen timing to wind patterns risk extinction. Even early human evolution bears the mark of these pressures.
favoring adaptability and creative problem-solving as our ancestors faced the chaos of changing skies. And air doesn't just shape individuals, it sculpts species. Dispersal through air might seem random, but it's often selective. Certain traits, body size, wing form, or even behavior determine who gets carried where. Over time, this non-random dispersal can drive populations apart, creating genetic diversity even within the same forest or coastline. The aerosphere becomes not just an environment, but an evolutionary laboratory. In the end, everything that lives on Earth is in conversation with the air above it. It's a silent dialogue between biology and physics, behavior and weather, evolution and chance. So next time you feel the wind brush your face, remember that breeze carries the whispers of migrating insects, the flight codes of birds, the pollen of distant trees, and maybe, somewhere up there, a spider drifting through the sky.
Air isn't empty, it's alive. And the more we understand it, the closer we get to understanding life itself. In the next episode of Foe's Curiosity, we'll travel back to the earliest days of humanity. How did our ancestors use air to tame fire? How did breath itself give rise to speech and language? Why did ancient hunters design tools that flew better through air long before aerodynamic theory existed? And what secrets lie behind the world's first wind-powered inventions? If you enjoyed this journey through the living air, don't forget to subscribe to Foe's Curiosity on YouTube and follow us on Instagram for more explorations into the science of life, motion, and wonder. Until next time, stay curious.